So hello, in today's video, we'll talk about the complexity of algorithms using frequency counts, and we'll be using pi approximation algorithms to demonstrate this. For this presentation, we'll only be using one pi approximation algorithm, but I will show you different variations of it. For each variation, we'll explore the caveats, possible optimizations, the frequency count, and how close the approximation is to the actual value as input size increases. Finally, the overall time complexity. So we'll be using an algorithm that makes the use of summing a circle's area. So here's the visualization of the algorithm. So let's first try to understand the concept using this visualization. You can observe that this is just a quadrant of a circle that is situated at the first quadrant of a Cartesian plane. So the idea here is that as we put more random points on the plane, the red dots will eventually cover the area of the quadrant, thereby being a good representative of the circle area. As for the area of the whole square, you can obtain it by summing the number of blue dots and red dots. Now, how is this relevant to finding pi? Let's jump to the mathematical basis of the algorithm. We know that the area of a circle is pi r squared. But since we only have a quadrant representation, okay, it must be multiplied by 4 to get the full area of a circle. Okay? So the area of a circle was equated to the area of a quadrant multiplied by 4. Okay. Now let's represent this equation in terms of number of blue dots and red dots. So the area of the quadrant is the number of red dots. Yes, can be seen here. Area of the quadrant, number of red dots multiplied by 4 is equals to pi times r squared, being the area of the whole square in this graph, is the sum of the blue dots and red dots. So with a bit of transposition, we can actually obtain the value of pi, which is equal to 4 times the number of red dots divided by the sum of red dots and blue dots. Okay. So before jumping into the code, let me clarify that all variations that will be presented are defined as functions that receive an integer, which is an input size, and returns an approximated pi value based from its calculation and the frequency count, the number of steps it took to actually calculate this value. So I also have a notebook here, so we can see this for demonstration purposes. I imported pyplot, math random, and numpy. I also defined two helper functions. So the first one is to plot the frequency count, the graph, and also the approximation on how close the value is to pi. Okay. And here are the variations, which will be discussed later. And I also have a runner function for the testing purposes to see the frequency count. Okay. So the first parameter is the algorithm itself. So it's a function reference, which we pass in the input size, as mentioned a while ago. Okay. Then this function is also in charge for iterating to make the input size bigger. Okay. And it also does the plotting. So I just call this and pass the function in and the starting input size and the number of loops. So it's easier to test. Okay. So let's start. So for the first variation, we initialize our counters, and then we iterate through all integer valued ordered pairs in the square area set by the radius parameter. Okay. And then for each ordered pair, we perform a check to see if it is inside the bounds of the circle or not. We then increment the respective counters and the frequency count by 2 to see, since an if statement will take one step, And then whether it be true or false, the executed statement is only one. Okay, so the total is two. So due to the nested for loops, with each one iterating from 1 to n, this algorithm has a time complexity of O(n) squared. Before showing any graphs, let's try to optimize the code. We can see here that for each y value, x squared is calculated repeatedly. So is the radius squared. Okay? It's better to reduce the amount of repeated computation. So let's see in our semi-optimized version, we store the square of the radius in r squared and the x squared in x squared. Okay. So when it comes to each y, we only have to access the values that were previously computed. Okay. We don't have to make repeated computations. As seen here, we have stored the values in respective variables. Unfortunately, it is still an O(n) squared algorithm. To some, this may seem like a fully optimized code, but we can actually optimize this further. Yeah, but for this, we need a bit more analysis. So our current algorithm generates an ordered pair and tests if it is within the quadrant's bounds. Okay. What if we are able to immediately obtain a count of ordered pairs that fit the condition given an x-axis value? So let's see how. Um, for an example would be if I were to give the value 4 as the x value, I would immediately be able to obtain 4 as the number of blue dots. Okay, so is it possible? Okay, let's see. Our test condition to see if a point is within a circle is the equation x squared plus y squared must be less than or equal to r squared. Let's just do some simple transposition to obtain y. So it's less than the square root of r squared minus x squared. Since variation 1 focuses on integer valued pairs, let's get the floor of the answer. Note that we don't obtain the ceiling because this might lead to a greater y than what's allowed by the circle's bounds. Okay. So this represents the max integer value of y that will not exceed the circle given an x coordinate. For example, given the value of 4, okay, we are limited by the y value of 3. Okay. So given the x value of 3, we are limited by the y value of 4. So given the x value of 2, we will not exceed the bounds of the circle. Okay. We are only getting the integer value within. That's our max y. So remember that this is only a y value, but we need the count of blue dots, not the y value. So we add 1 to the floor value, which makes sense because the y value is only the distance, but we need the count of blue dots. So for example, here, okay, so at the x equals 5, we still have 1 dot, which makes sense because um, the perimeter is still counted in the area of the circle, okay? And we know that y is 0 at x equals 5, okay? But we still have to count that 1 dot, so we have a plus 1. So the same can be said for x equals 4. We know that at x equals 4, the y must be 3, okay? But here we have 4 dots because we're also counting the dot at the baseline, which is to be counted naman talaga, okay? So the actual count is 4. So we have a plus 1 at the end. Okay? So that's the number of blue dots. So how do we obtain the number of orange dots, the dots outside the circle? Okay, so we obtain that by getting the radius and subtracting it by the number of blue dots. Now let's try to carry over this logic in code. So in the optimized variation, We iterate through each x coordinate, obtain a count using our previously discussed equation, and increment the appropriate counters. As you can see here, we add the number of blue dots and we add the number of orange dots outside. So we instead increment the frequency count by 3 since we have 3 operations. Okay. So it's amazing. We managed to remove a whole loop, and that will leave us with an algorithm of linear time complexity. Okay, let's now try to test our variation 1 algorithm. Since it's linear in time complexity, we can start with a much larger input and 8 number of loops. Why not? Okay, so let's play. And we obtain the results. And here are the charts. Okay. So let's see the approximation values outputted by the function. As seen on the table and graph, we are very close to the true value of pi as the input size increases. You can see also in this graph, it's converging. As for the frequency count, the graph shows that the algorithm does indeed have a linear time complexity. So as input size increases by 2, so does the frequency count. Okay. Let's now view a brief summary of the pros and cons for the first variation. First is that it's fast. Having a linear time complexity is quite impressive. Second, it's deterministic, since we generated the points evenly across the Cartesian plane. Fortunately, this algorithm is prone to integer overflow problems due to having to calculate the squares of numbers. So an overflow will be encountered once the input value is high enough. So let's move on to the next variation. Here, instead of receiving the radius of a circle as the parameter, we receive a sample size. Okay. And for each sample in the sample size, we generate a random x and y value. That's between 0 and 1. So it's a floating point value. And then we fix the radius of the circle to 1. So it's a unit circle. So basically, we're obtaining a random point within a unit circle, a unit square rather. Okay, so the point can be outside or inside the unit circle. Um, we then repeat the same condition, similar to our previous algorithm. So the square added to another square, it must be less than or equal to the radius squared, which is still 1. And then we increment the um, respective counters. Okay. And then the frequency is incremented by 4 as there are 4 operations, generating the random numbers too. So one here, then another one for the if condition, and another one for the executed statements. So as you can see here, there's only one loop, okay, to obtain n random ordered pairs. So this algorithm is also linear in terms of time complexity. Now let's try to test again, variation 2 this time. So it's also linear, so we can start with a large input, greater number of loops, why not? And here are the results. So the approximation results may be a bit weird and inconsistent as the curve is not smooth. This is more or less expected as the generated points are not uniformly distributed. They're just random. So points may appear more frequently outside or inside the circle. Don't know. Okay. So in this graph, we can see that the frequency count is indeed linear, that the frequency count is just 4 times that of the input size. It's also linear. So based on what we've learned from variation 2, we can conclude that this algorithm is also fast, having a linear time complexity, similar to variation 1. It also prevents overflows as the values required are just between 0 and 1, just floating point values. Yet there is still a caveat. It is non-deterministic. Generating random points do not provide a uniform distribution of points within and outside the circle's area. Hence, the computed value does not necessarily get closer to pi as we increase the sample size. Okay. So now we have the last variation. This algorithm, we again iterate through ordered pairs, similar to the unoptimized version of variation 1. Unlike in variation 1 though, we retrieve the ratio for each coordinate to the given radius and use the new values as the ordered pair. We can see that here where we divide x by the radius before you square it, and then we divide y by the radius before you square it. Okay. So using this method, we will be able to obtain ordered pairs with floating point values between 0 and 1, but they are distributed evenly inside the unit square. Again, for each ordered pair, we test if it is within the unit circle or not and increment the appropriate counter. So the frequency again is incremented by 2 because this statement is takes 2 steps. Unfortunately, we won't be able to apply the same optimization we did for variation 1, which, if you forgot, was computing the count immediately. The reason being that this relies on floating point values, and we know that there are an infinite number of real points between 0 and 1. Okay. Okay. So lastly, let's try to test our variation 3, see if it gets closer to pi. So it has polynomial time complexity. So we'll start with a smaller input so can finish fast. Yep, we'll have to fast forward this video a bit. Okay, so it just finished. Wow, 6 minutes. Okay, so here's the outcome of running the algorithm. We can see that the graph does converge to the true value of pi as input size increases. Okay. However, the time complexity is O(n) squared. We can already see that in the code as it has a nested for loop with each one iterating from 1 to n. This is also evident in the table values. Okay. As n is doubled, and the frequency count is quadrupled, which means that this is much, much slower than the first two variations. Now, to recap the third variation, we saw that it having a polynomial time complexity is much slower than the first two. But again, it does prevent integer overflow as we rely on values just between 0 and 1. Finally, it is also deterministic as we generate points evenly across the unit square. So let's try to compare all three variations. It is interesting to see how each variation fails at one factor. It's like there has to be a trade-off if we were to improve a certain aspect of the algorithm, which is a very common occurrence in the field of computer science. We usually trade off more memory space to gain an increased performance because memory is much cheaper nowadays, similar to what we did in variation 1, where we just store the value to avoid computation. We chose to make the algorithm faster by using more memory. Okay. So that concludes my presentation. I hope you learned a lot from this. So thank you and see you next time.